Swayam Prabha. Digital India. Educated India.
Welcome back to Mechanics and Control of Robotic Manipulator. In the last lecture, what we have seen how to derive the equation of motion using simple Newton-Euler method. In this particular lecture, we are going to see the same thing with the help of Lagrange-Euler, again Matlab environment. So in the sense, what we are trying to see here is, so we are actually like trying to recall what is Lagrange-Euler method and how we can put it in a Matlab. So the same example we are going to take. But before that, let me actually like recall what is the equation is coming here. So here you can see that the L is a Lagrangian, which would be kinetic energy minus potential energy. However, when we try to derive the tau I, so it is having two different things. One is actually like the partial derivative, the other one is actually like time derivative. In the sense, so you have to actually like write the you can say Matlab code, which is actually like mixed of everything. So that is what actually like one of the complexity. However, if you go with Mathematica or probably Maple, it may be actually like straightforward. However, so since we started with Matlab, we will actually like see how to do it in Matlab itself. Okay. So in that sense, we are actually like trying to recall what is Lagrangian, and we will see like how we can derive the kinetic energy and how to derive the potential energy and all. So now based on that, the same example we will take. And right now, what are the things will come? So you need to find out what is the center of mass, or you can say location of center of mass m1 and m2 we need to find, which is we have written as x1 and y1 and x2 and y2. So now we need to take the derivative of that, so which is x1 dot, y1 dot and x2 dot and y2 dot. Once we derive this, so based on that we will actually like go with what you call kinetic energy and potential energy. Once we obtain that, then we will take the time derivative, or before that partial derivative, then we will do the time derivative and we will map the equation. So in that sense, what we are trying to do, first we are trying to find out what is the location of center of mass. So for finding that, we can use again the same equation what we have used in the DH table and DH representation. Your forward kinematic model will give you can say location of center of masses, which I have taken already. PC01 is a location of center of mass of link 1, and PC02 is for 2, link 2. So this is we all actually like recall. This is straightforward. This is equivalent to x1, this is equivalent to y1, and this is x2, this is y2, and z1 and z2 are 0 because it is in a plane. Right now, what we are actually like calling, the theta 1 is function of time, and we say that the t is actually like time, which is actually like real variable. So a1 and a2 are constant, but theta 1 and theta 2 are time dependent variable. So in that sense, what one can actually like do, so we can actually like take the velocity of center of masses, simply take the time differentiation. The time differentiation I am doing as a difference as the command or the function in Matlab. So PC1 comma time, in the sense I am taking time as the variable. So I am actually like differentiating the PC01 with respect to time. So now what this will give, VC01 and VC02 will give the velocity values. So that velocity value I am actually like rewriting in theta 1 dot and theta 2 dot manner. So now what I got, VC01 and VC02, and now what I wanted the kinetic energy. So the kinetic energy is actually like you can say half into m Vc1 transpose Vc1, okay, Vc01. So this is what we have seen how to write in a you can say syntax, and the similar way the second link kinetic energy also. So here fortunate there is no rotational kinetic energy, so we can actually like leave it, only the translational kinetic energy we have taken. Similarly, the potential energy, what that would be, the y1, right, because it is actually like vertically down, the y1 we need to write. So the y1 is actually like PC01 of 2 is y1, y2 is PC02 of 2. So in the sense, so I hope there is a typo, this is m2. So I will correct it in the Matlab code, and in the handout also I will correct, this is so m2. Okay. So please correct that, this is actually like m2. So in that sense, the potential energy is actually like giving this point. So the Lagrange is actually like kinetic energy minus potential energy. So we can actually like write. So now what we need to do, we need to do the partial derivative. For doing the partial derivative, once you know the what you call the kinetic energy and potential energy, you calculate Lagrangian. Then you take the partial derivative with respect to theta 1 and theta 2 and theta 1 dot and theta 2 dot. So these all need to be done in a separate file, because earlier what we defined theta 1 is function of time. So now here it is actually like without, it is actually like independent variable. That way only we are considering. So now in that sense we can actually like derive this. So once we derive the theta 1, or you can say dou L by dou theta 1 dot and dou L by dou theta 2 dot would be coming into this way, and this we can actually like rewrite, and then now we are actually taking the time derivative. So once you all do this, so what you can actually like see, you have already take dou L by dou theta 1 and dou L by dou theta 2. So then you can actually like simply substitute it and then do it. Since these equations are lengthy, I have used one file transfer. So in the sense, this simple Matlab code itself, I have tried to explain all the background work. Okay. So in that sense, we can actually like write this equation in this form. So you know dou L by dou theta 1 dot. Okay. So then actually like I can take the time derivative also. So in the sense, dou L by you can say dou theta 1 dot, I have taken time derivative in the sense d of dou L by dt of dou theta 1 that I have taken. So in the sense, this is what the case, and this is dou L by dou theta 1. So this minus of this would give tau, right. So this is what we have taken. So now tau 1 and tau 2 we have obtained. So now these are the bigger equations which we have actually like obtained. So this is the equation which we obtain even in the new, you can say Newton-Euler method. You can recall this is what we obtain in the Newton-Euler. So now in that case, if we go to Matlab environment, what we need to do? So we need to actually like do it several things. So what first? So first we need to actually like calculate what you call the velocity. Okay. So this is what we did in the first Matlab code. So I have assumed that the theta 1 and theta 2 are time dependent. So I have actually given PC1 and PC2. So now I actually like differentiate with respect to time. If I run this, you can actually like see why I am actually like doing it here. Okay, I'll actually like make it one more command just for your benefit. Okay, so clear all and close all. Anyhow, close all is not required here because there is no figure window here. So now I actually like just run this code. So there were no error command. So you can see like in this case, so VC1 and VC2 is coming. So this is what I was saying, the assumption is actually like constraint, because we assume that theta 1 and theta 2 are function of time. That is what it is giving a warning. It can be actually like you can write theta 1 equal to symbol of theta 1 of time also you can write, then this warning will not come. But for betterment, you can actually like write it as per the earlier definition itself. So now you can see here, this is giving us a difference, right. So now this difference of theta 1 of t comma t is supposed to be theta 1 dot. So for that I copy this, okay, and I rewrite that, okay, I will write that here. So I copied this and I rewrite that as a theta 1 dot, okay, and here theta 2 dot, and the potential and energy I said the typo is there. So this is the correction. So now you can see that the kinetic energy we calculated, potential energy we calculated, and the Lagrangian we have calculated. So then you can see here, so the theta 1, theta 2, theta 1 dot, theta 2 dot, all independent variable, in the sense it is, there is no time as a t as defined. So now if I actually take this dou L by dou theta 1 and dou L by theta 1 dot will be found, right. So now if I actually like do this, okay, so what I will get a bigger you can say equations, right. You can see like this is dou L by dou theta 1 and this is dou L by dou theta 2, okay. This is dou L by dou theta 1 dot and this is dou L by dou theta 2 dot. So I just wanted to show, you can see, right. So now these two are actually like supposed to be taken as a time derivative. What one can do, you can actually like copy these two terms, and then you can say that theta 1 and theta 2 are time dependent. So that is what we are actually like doing it in the third thing. So you can see, so here, so I am writing as theta 1 dot and theta 2 dot, and theta 1 and theta 2 all are actually like time dependent, right. So I will actually like even make it, because I run it as actually like independent. So I will write it clear all and close. So okay, so now you can see like this is what we have obtained, and I am taking a time derivative. Okay, that time derivative I am actually like putting into one simple, you can say, file. Okay, so that file I am actually like writing it theta 1, okay, dou 1, so that I can show the other one. So now if I actually like run this, what it will give? So it will give the time derivative of these two terms. Okay, so now I will actually like run this. Okay, so now although the display in the you can say command window, okay, the command window will actually like come. Okay, so but what I have actually like made it, I actually like made it for what you call in the file also. So now in that sense I actually like open this simple underscore d and dou theta 1, for example. I just open that. I hope simple, so I can actually like see that is all file. I'll just, you can see, right. So now this is actually like having a difference command, because you see like we have taken time differentiation. Now probably you would have already realized that what is the benefit of what you call Newton-Euler method. You see, Newton-Euler method, we did not go back and forth, we did not create these number of files, right. So now you can see this n1 and n2, which is actually like we have written, so which is equivalent to that time derivative, that is having, you can say, time differentiation of theta 1 dot, theta 2 dot, and it is having everything is actually like time dependent, right. So this you have to copy and replace this theta 1 differentiation as theta 1 double dot, and differentiation of theta 1 of t comma t as theta 1 dot, like that you have to modify. So you can see like here these all variations and modification you have to do. So when I actually like copy this and modify, for example, if I say this, so I call this is control F, if I put, so this theta 1 dot of this differentiation I can write as theta 1 double dot. Okay, so then what you can actually like see that I can actually like replace everything, so then that would make. So now the similar way I can actually like modify this theta 2 double dot as this form. So now you can actually like see that these all actually like modify, right. So this modification I have already done, and you can see right now this time differentiation I already modified, and if you actually like see here, there is no function of time anywhere, right. So now if you look at it even till the end, so there is no time dependent variable. So now what you can do, you can actually like take tau 1 and tau 2 in this form. So now if I actually run this, so if I run this, so what I can actually like get, whatever I have seen in the earlier case, the tau 1 and tau 2 is obtained the same form, right. So only thing, it is not simplified. So if I actually like say simplify of, so tau 1, so you can see what you have actually like obtained in the previous lecture, the same thing is coming. For example, you want to see what is the centripetal term L1, L2, M2, sine theta 2, which is a minus sign, the same thing is coming, right. So instead of L1, L2, we have taken A1 and A2. Similarly, the Coriolis component, so 2 times of A1, A2 cos theta 2 into M2, so that is also coming, right. So similar way you can actually like find, so every other thing, so even you can actually like simplify tau 2. So you can see this is also like coming as per that. So here you can see like only the you can say centripetal term would be coming, that is you can see, which is actually like A1, A2, M2 sine theta 2, that is there, and you can see the gravity term also coming. So like that you obtain. In the sense what you can see, so the same result both formulations are giving, But the formulations, if you talk about computational perspective, even I am not talking about numerical computation. I am saying even you are deriving the equation of motion in symbolic form. Personally I felt that Newton-Euler is giving much more flexible. In addition to that, that can be even give all, you can say, 3 axis forces and 3 axis moment, which can be used for structural dynamics as well. Further, even you can go up to the 0th joint or 0th frame, then you can even transfer what is the, you can call shaking force and moment. So based on that, you can say like your end effector is taking this much load, your base supposed to be stronger this way. For example, you are putting into a mobile base, so your end effector is lifting something, your support reaction is not enough, what happens, the vehicle will topple, right. So in that sense, if you calculate this end effector to base forces, the shaking forces and moment, the support reaction is directly coming. The support reaction all the time is positive. If the support reaction is giving a negative sign, what in the sense your manipulator is losing the contact from the ground. And similar way, if the shaking forces and moments are known, you can actually like decide what, you can say, support you should have or what foundation you should have, and whether we can mount it on the vehicle or mount it on the table, or your foundation should be strong and other thing. Okay. So these all ideas will give, and Newton-Euler even will give the axis or axial forces and moments. So in that sense, even you can do the structural aspect, you can go for simple dynamic design study, and then you can see what would be the cross section better, better cross section for supporting this load or this mass and all. Okay. And that idea will always better. So in that sense, what we have seen in this particular lecture, so we have talked about how to derive the equation of motion with the help of Lagrange-Euler using Matlab code. That is what we have seen. So I hope in the next class we will see the numerical simulation of a dynamic model, and then we will actually like close this dynamic part, and then we will move to the controller and trajectory generation. So with that, see you then. Bye. Take care.